to look at ellipses, and we're going to be focusing on graphing ellipses, writing equations of ellipses, finding the coordinates of foci, and completing the circle to do that. So first, let's define an ellipse. An ellipse is a set of all points in a plane such that the sum of the distances from any point on the ellipse to two, actually it shouldn't say to any, it should say two given points foci is a constant. So here's my one foci, and here's the other one. Okay, I've got F and G, and it's that this plus this is the same as any other two ones I do. So if I went like this distance added with that distance, that's going to be the same as well. So what this will look like visually is something like this. You can see those two foci. They kind of are in the spot of Stewie Griffin's eyes. And every point on that ellipse, those distances, that blue one and that red one, sum up to the same thing. It always adds up to 10 regardless of where I am around the ellipse. You can also visualize this because all conic sections are the intersection of a plane and a double cone. You can see on my double cone over here how I have my plane on a slant to create that ellipse. So, some vocab, and we saw some of these vocab the other day in Desmos, but the major axis is the longer diameter, the minor axis is the shorter diameter. That's point on the ellipse to point on the ellipse. We have vertices, those are the endpoints of the major axis, and covertices, that's a new one, that's endpoints of the minor axis. We have our two different orientations on an ellipse. We can have a vertical ellipse, or that egg kind of shape, or we can have a horizontal one. That looks more like Stewie Griffin's face. On my pictures, you can see those major axis is this entire length. We also have a longer radii, and that's just from the center over. And our minor axis is the other directions, the whole length, but this is the minor radius. So pink is the minor axis. The shorter radius is like right just here. Okay. So now let's take a look at graphing. We're going to need to find the center, the vertices, covertices, major axis length, and minor axis length, and sketching a graph. We did this in Desmos, but we had Desmos do the graph for us and then set the statements. So here I'm going to kind of do it the other direction. So my center here is at 0, 0. I like to put a little X at my center because I don't like to put a dot because the ellipse isn't going to go through that. Now these denominators, they are going to tell me how far to go, but I'm not going to head 25. I'm actually going to head the square root of that, or 5. So I'm going to head 5 in each direction. So that's telling me that the longer radius, 1, 2, 3, 4, 5, sorry, the longer radius is 5. So if the longer radius is 5, the major axis length is 10. 10. Then on this one, the square root of 9 is 3. So that means I'm headed 3 up and 3 down. And so the minor axis length is 6. So the shorter radius is 3, minor axis length is 6. And so my ellipse is going to look like that. And then my vertices, that's these points that I have in red. So that's at 5, 0 and negative 5, 0. And my covertices, those are the points I did in green. 0, 3 and 0, negative. And we sketched our graph. Done. On example 2, I now have something that's translated. And you can see it's translated because there's a piece with the x in that quantity squared and a piece with the y in that quantity squared. So my center here is at, the center is determined from these two pieces, and it's opposite on both. So we'll have it at 1, negative 4. 1, 1, 2, 3, 4. Again, I'm going to put a little x because I'm not going through that point. Now, along the x on this one, I'm going to head 4. 1, 2, 3, 4. So that's the square root of 16. 1, 2, 3, 4 in either direction. And my y's, I'm going to head square root of 36, or 6 in each direction. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now notice this is more of an egg shape. So my major axis is actually that y value. So our longer radius is 6, which means my major axis is 12 units in total. Those vertices are at, a minute. Our vertices are at 1, 2, 1, 2. Notice here I don't have 0 plus or minus 6 because I've translated it this time. And then the other one is at 1, negative 10. And then my minor axis is going to be, it's 4 on this side and 4 on that side, so that's 8 units in total. And then my coordinate points are going to be 5, negative 4, and negative 4, We can also write the equations. That was our second objective. And so when I'm writing the equations, I'm going to start by finding the center. Here my center is at 0, 0. So that tells me I'll have x squared, y squared, both with denominators on the bottom, a plus sign between them because we're not doing hyperbolas yet. And the distance that I traveled here from 0 to 7, well, that's 7 units. So one thing to keep in mind, when I went from my equation to the graph, I had to square root it. So when I'm going from my graph to my equation, I'm going to have to square it. So 7 squared is 49. Now this direction, it's 25. Now, not to be confused, we still have to square that. Even though 25 is a perfect square, I need to square it again, put it in the equation. Okay. So to recap, I determined the center, determined how far the ellipse was in each direction, and filled into my equation. And remember that those values in the denominator are distances squared. So back to this one. It is a little trickier to find my center on this one, but what I like to do is I like to just kind of draw in that minor axis and draw in that major axis, and where they intersect will give me my center. So my center is here at 2, negative 1. Let's label that. Now I am headed 1, 2, 3, 4, 5 along this length. Okay, and I am headed 3 this way. So when I set up my equation, I'm going to have x minus 2 squared over 5 squared, which is 25, and y minus negative 1, so that'll be a plus 1 squared, over 3 squared, which is 9 plus 1. And both of these equations you could toss into Desmos and see if it actually comes out as the graph, but it should. Now, foci. Foci are those 2 points that help define the ellipse, and they lie on the major axis, or that longer axis, and they're equally spaced on each side. If we think back to this picture of what's happening, I don't know if I'll be able to draw it. Okay. Right here is one of our foci, and singular is focus, and here's the other one. Again, to me, they look like either Stewie Griffin's eyes or Baymax's eyes. So, back to what we're looking at. We want to find the foci. Now, this is that same ellipse we did before. I'm just going to make a quick sketch. I like to have a visual. This whole unit is like taking geometry and algebra and putting them together very nicely. And the visual is really important. All right, so we have this length here is 25. 5, sorry, squared is 25. Is 5. And this side is 3. Now, we know it has to be inside the ellipse. Stewie Griffin would look very weird if his eyes were not in his head. And the way we're going to do this is we're going to take our shorter radius squared plus our foci distance. squared is going to give me the longer radius squared. So this is really just the Pythagorean theorem. A squared plus b squared equals c squared. My shorter radius is 3. My foci, I don't know, so I'm just going to use f for the moment. And my longer radius is going to be 5. 9 plus f squared is equal to 25. Now, if you look at this equation and compare it back to the original problem we're looking for, you should recognize some of those numbers. So our foci are plus or minus 4, and so that's telling me the foci are 4 units from the center on either side on the major axis. 1, 2, 3, 4 right there, and 1, 2, 3, 4 right there. This one definitely looks more like an alien. Okay, so our coordinates for our foci, because we always write them as coordinates, is 4, 0, and negative 4, 0. We're going to do the same thing on this one, but if I look at this equation, it looks very different. All of our equations before now have all been equal to 1 on the other side. This one doesn't have that. So I'm going to start by dividing by that 3,600. I know it looks intimidating, but you get 1 on the other side. 36 over 3,600 is really just 1 on the top and 100 on the bottom. Perfect square. That's convenient. And 100 over 3,600 will be y squared over 36. So now my center is at 1, 0, right here. We're headed 10 on our x, so I'm going to be off by 1, but that's okay. I'll survive. And then 10 this way. And I'm going to head 6 this way. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so there's our graph. The larger they are, the worse they look. Just how my graphing ability is. So now I'm going to do my shorter radius squared plus foci squared is equal to longer radius squared. So shorter radius is 6 squared, f squared, 10 squared. Pause for a moment right here. Make sure that my numbers match with my denominators, and they do. And a reasonableness check. I shouldn't have 36 on the other side because that wouldn't make any sense. It would give me f squared equaling a negative. Back to working. F squared is equal to 64, so f is plus or minus 8. However, that's just how far away they are, not my answer. So my answer is going to be the coordinate points. So we want 1, 2, 3, 4, 5, 6, 7, 8, a point right here. And 1, 2, 3, 4, 5, 6, 7, 8, a point right here. So we're looking at the coordinates of 9, 0, and negative 7, 0. Because again, I had that different center, so that's why it's not just plus or minus. So take a minute, try example 6 on your own. Did you try it yet? Make sure you actually try it. Pause the video, it's okay. Here's the answer. Our foci are at 6, negative 3 and negative 2, negative 3. We can also find the foci from a graph, so you try this one as well. Go ahead and pause the video. So, with our center at 0, 0, the foci on this one ended up as 0, 24 and 0, negative 24. I bet a lot of you didn't think that those were going to work out with nice integer values, but they did. It is possible to have foci that land on a radical or an irrational answer. If that's the case, you want to leave it as a reduced radical. All right. So last objective was to complete the square, and I'm going to start by completing the square on a circle before I do an ellipse, just to review that. So when I'm completing the square to rewrite, it's basically that someone's taken those set of parentheses that had quantity squared and expanded them out already for us. So the first thing I'm going to do is organize my term. So I put my x's together. Oh, it's minus. My x's together. And then I'm going to put my y's together. I'm also going to take that negative 12 and move it to the other side by adding it to the other side. So I've moved the negative 12 to the other side, and I've organized my pieces. Now I need to find some number that makes this a perfect square, the blue section a perfect square trinomial, and a number that makes the green one a perfect square trinomial. So long as I have a 1 in front of that x squared, you might remember a trick from Algebra 2 or from Algebra 1, where you take that middle term, divide it by 2, and then square it. So negative 6 divided by 2 is negative 3, squared is 9. That's going to create a perfect square trinomial. But I can't just add it to the left side without also adding it to the right side. I'm going to do the same trick. 4 over 2, and then square it. 4 over 2 is 2, 2 squared is 4, 4, and add 4. Depending on who you had for Algebra 1 or Algebra 2, you may have seen why it's half and squared. It's a real interesting thing with algebra tiles. If you're interested, I can show you afterwards, or I can even make another video about that. So the first one factors to x minus 3 quantity squared, and the second one factors to y plus 2 quantity squared. And then I'm going to combine all the pieces that I have over there. I have a 12, a 9, and a 4, which conveniently comes out as 25. How that's awesome. Now, so my center, again, we're doing opposite and opposite, is 3, negative 2. And my radius is the square root of 25, or 5. 1, 2, 3, 1, 2, and we're going to go 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And there's my circle. Not bad on that one. I think that's the best looking one so far today. All right, so now let's take a look. This one actually happens to be an ellipse instead of a circle. And I can tell right off the bat that it's an ellipse because I have different coefficients. See how I have a 1x squared and a 25y squared? Those different coefficients are telling me I'm going to end up heading different amounts in either direction. Okay, but the same process is going to still go into play. I'm going to still organize my pieces, my x's together, and then I'm going to organize my y's together. And I'm also going to take that constant and move it to the other side. Now, before I complete the square and have my boxes, I have one other thing I have to do. And remember, this half and square trick only worked because the coefficient is a 1. I have a coefficient of 1 on my x's. I do not have a coefficient of 1 on my y's. So what I'm going to do is I'm going to, just on the y pieces, factor out that 25. Okay, so, and I can throw some parentheses around that just to clarify what's going on there. So now I have x squared minus 6x. What will go in that first box will be 9, because half of 6 is 3. 3 squared is 9. And I have 25 y squared minus 4y. And I'm going to put a 4 in that one. Oh, that was a negative 84. That would have been a catastrophe. So my 9 that I added here, I have to add to the other side. Now, I have a 4 inside my parentheses, but it's not actually a 4. This is the biggest mistake people make on these. Well, it's either this or forgetting to add to the other side altogether. It's 25 times 4. 25 times 4 is 100. And that's how much I'm going to add to the other side there. I factor each piece. X minus 3 squared. And then 25y minus 2 squared. and combine on that other side. And I get 25. So before I can go any further, since it's an ellipse, I need it to equal 1. So I'm going to divide each piece by 20. X minus 3 squared over 25. My 25s are canceling here, so this is kind of like y minus 2 squared over 1. I'm going to write the 1 normally. It's kind of an invisible one. It doesn't need to be written, but I think it helps with all of that. And so my center is at 3, positive 2. And so 1, 2, 3, 1, 2. I'm going to head 5, 1, 2, 3, 4, 5 in either side of that. 1, 2, 3, 4, 5. 1 in either side on that. And that'll make this lovely ellipse, which is fairly flat. Okay. And from there, depending on what the question asked, it said on this, I just graphed. We could also answer that the major axis is 10 units long, just like we did in our first problems. We could say our minor axis is 2 units long. We could have our vertices are at 8, 2 and negative 2, 2. We could have our co-vertices are at 3, 3 and 3, 1. And then we can even find our foci from that. So let's do that. We have 1 squared plus f squared is 5 squared. This is good because this is an irrational one. F squared is 24. So f is the square root of 24, which we reduce to 2 root 6. So my foci are going to be located 2 root 6 from the center along that major axis, along that x length. So we're going to have 3 plus 2 root 6, 2, and 3 minus 2 root 6, 2. Just going to be like right there. It's going to be really far apart. Because the further apart the foci are, the less circular it looks. The closer the foci are together, the more circular it looks. And if the foci are in the same spot, boom, that makes a circle. And that spot is the center of the circle. So then there are 2 more problems for you to try. So pause the video and try those 2 on the last page. So here are the solutions. I'm sorry that one ran off the graph. So you might have scaled your graph to be every other. And okay, and that concludes today's lesson on ellipses.